Okay. Hi, everyone. My name is Jennifer Butler. I am a full-time CT and nuke med technologist, and today I'm going to be talking about the science behind the big donut, which is the CT scanner. And I'm going to talk about how it works, how it was developed, and then we're going to go into some interesting cases, and I'll talk about what it's like to be a CT technologist. And then I will be happy to answer any questions that y'all have at the end. So what is this donut? CT has also been referred to as a CAT scan or a CT scan. The terms are kind of used interchangeably. The CAT scan was when it was first developed. They called it a computed axial tomography because the axial plane was the only plane that the scanner was able to give us. But since developments have been made, they have dropped the axial because now we can see it in different planes. So it's actually called computed tomography now, but you'll also hear people call it a CAT scan. So CT is a subdivision of radiology. Within radiology, we have X-ray, nuclear medicine, ultrasound, MRI, and a CT is basically just a really quick way to get a detailed image of the organs and tissues inside the body. CT does this by combining X-rays and computer calculations to produce the images. So now we're going to talk about an X-ray versus CT. So X-rays are only 2D. They are not able to distinguish between two tissues of similar densities. And the CT, it uses a narrow X-ray beam and it rotates around the body, producing cross-sectional images, which gives us a lot more info as opposed to the 2D. With CT, we're able to differentiate between tissues of similar densities. So here's just a picture of the difference between an X-ray and a CT scan. The top two pictures are chest X-rays, and you can see that you can't really see very much anatomy. You can kind of see the bone structures, you can see the heart, but everything else just kind of looks shadowy. The two bottom pictures, you can see a lot more detail within the chest. You can actually see the different arteries. You can see the IV contrast. That's why the vessels here look so bright. That's IV contrast. Here we're seeing a vertebrae in the back. And then over here, we're seeing shoulder blades, and these are the ribs. So you just get a lot more detail as opposed to just a regular X-ray with the CT scan. So just a little background about CT. It was developed by Godfrey Hounsfield in the 1960s. That's when he developed the first CT scanner. And in 1971, the first CT scan was performed on humans. After the CT scan is performed, it requires a lot of mathematical techniques that convert the CT data into images. And this was developed by Alan Cormack. The early scanners that were used in the early 70s were only limited to the brain, and these scans would take about 20 minutes. Now we can do these scans in about 3 minutes, so that's quite a significant drop in the time that it takes to do the scans. In 1974, Robert Ledley developed the first whole body CT scanner. By the late 70s, many hospitals had CT body scanners. So just a look at the generation of CT scanners. The first generation was just one detector and a pencil beam, and the scan would take about 4 minutes. The second generation, which is over here shown by B, they use multiple detectors and multiple pencil beams, and that would take about 10 to 20 seconds per slice. The third generation, which is what we mainly use these days, it has multiple detectors at the bottom here, and it uses a fan beam for the X-ray. So we're getting lots of different viewpoints with the X-ray beam, and they strike multiple detectors that you can see at the bottom. The fourth generation of scanners kind of came around the same time that the third generation scanners did, and they use a stationary ring of detectors that the X-ray beam just rotates around the patient and takes pictures. And both of those just take a few seconds. So here's a look at just the whole process of the CT scan and what happens. So essentially, the patient is put on the CT table that you see here. They're put into the CT gantry. The scan is performed where we get attenuation measurements from the X-ray beam. That's converted into digital data, which is then sent to a computer for processing. The computer converts those that data into CT numbers, we call them Hounsfield units. That is then sent to a display monitor. And from the display monitor, we send those images to PACS. And all of those operations are done at the CT operator's console. So CT images are formed by three main steps. The first one is data acquisition. The second is image reconstruction. And the third is where we display, manipulate, store, record, and communicate the images. The main step that we're going to be focusing on today is how we acquire the images, which is data acquisition. So here's just a picture of the CT scanner that I work with every day. Here you'll see the table, and this is the gantry. It was made by Philips, as you can see at the top. The patient just lays on this table, and then we raise the bed up and slot them into the gantry there. So what do you have inside the gantry? We have a lot of different things, and this thing rotates very quickly. So up here, you can't really see it, but number one, that's the X-ray tube. That is what generates the X-rays. Right beneath that, you have the filters and collimators. The filters and collimators filter the X-ray beam, but they also shape and restrict the X-ray beam. Over here, you're going to see the internal projector. Over here, number 4, it's the heat exchanger. And number 5 is the high voltage generator. Number 6 is the gantry motor. That just causes the gantry to spin. So this thing spins, and I mean fast. Number 7 is the rotation control unit. Number 8 is the data acquisition system. Number 9 is the detectors, which is what the X-ray beams will hit. And then number 10, so this circle right here is the slip rings. And these slip rings are very important for the way that we do CT scans now. They allow us to basically spin that gantry really, really fast and then shoot the data from the gantry to the computers, but we don't have to use any cables. We use these slip rings instead. So they're kind of the window between the gantry and sending the data out that we're getting from the machine. So those are very important in our 3rd and 4th generation scanners. So how are the X-rays produced? This is where it gets very complicated. So I'm going to try to break it down here. So what basically happens is the X-ray tube produces the X-rays, and it does this by accelerating electrons from the cathode, which you see right here, through electrical voltage, stopping them at a target, which is the anode. The anode deflects the electrons, and 99% of the electron's energy is turned into heat that is absorbed by the anode. The rest of the energy converts the photons. The rest of the energy converts to photons with X-ray energy. These photons pass through an aluminum sheet filter, which absorbs the low energy photons, and then finally through the glass aperture, where we see the X-rays come out down here at the bottom. So basically, all this is happening. It gets really hot. These X-ray tubes are made of materials that have high atomic numbers and high melting points because they get so hot. So when the CT scanner powers up, the electricity in the scanner is inverted and transformed from AC to DC power. The anode and cathode are like battery terminals that supply 75,000 volts each to the X-ray tube at up to 1 amp. This equals 150,000 watts. So in order to generate the X-ray beam, it is like we're using 1,500 100-watt light bulbs. So in order to do that, you can imagine that it's getting very hot. So the X-ray tube is constantly being cooled using an oil-based cooling system. So after that, what happens next is basically the rest of the data acquisition. So the X-rays are generated by the X-ray tube. The X-rays fire through the filter and the collimator in a fan beam shape. They radiate and penetrate the patient. They hit the detector array. A scintillator converts the X-rays to visible light. The visible light is then converted into an electrical signal. And the analog to digital converter converts electrical signals into digital data. The digital data is then sent to the computer for reconstruction and display. So image reconstruction. This is basically when the computer manipulates the data collected by the detectors to create the CT image. It includes many different steps. It includes algorithms, Fourier transform, and interpolation. Basically what happens is the raw data is averaged and each pixel is assigned a Hounsfield unit or an HU. And we're going to get into more of that in just a minute. So with image display, we use either a cath ray tube or an LCD monitor. The digital to analog converter converts the digital signals from the computer memory back to analog format so that we can display them on the screen. When we display the images, we do it in 3 different planes. We do an axial, a coronal, and a sagittal plane. And the best way to describe these planes is to think of a loaf of bread. So the axial plane is every slice of the loaf of bread. If you stand the loaf of bread up and you do a front to back, that's the coronal plane. And then the sagittal, or I call it the side to side view, is when it moves from right to left. So you can see here, the sagittal plane is dividing the body into right and left sections. And the coronal plane is going from basically the front to the back of the loaf of bread. That's just the easiest way for me to think about these planes. So image display and manipulation. So the images are modified to make them more useful to the observer. Here you can see how we modify the images. So this first window here is a standard window. You're able to see the heart in great detail. You can even see the soft tissue around the lungs. This second window, it's the same picture, but you can see how you can see a lot more lung detail. That is what we call a lung window. This third image is a bone window, and you can really see the bones really sharp. We get these windows by basically changing the window settings. And we do that based on the Hounsfield units. So we control the window width and the window level. The window width is the maximum number of shades of gray that can be displayed. And the window level is the center point or mid-range of those shades of gray. So interestingly enough, the CT Hounsfield scale goes from -1,000 to about 3,000, where -1,000 corresponds to air and 0 corresponds to water, and 3,000 corresponds to dense bone. In an ideal world, the image would be displayed with a different shade of gray for each Hounsfield unit. However, even though there's more than 2,000 Hounsfield units, not all of these values can be displayed. Newer monitors can display up to 1,024 shades of gray, but the human eye can only differentiate fewer than 40. So in order to get these different pictures, we just change those window levels. But even though we have all of these levels of gray, we can't see them basically because we can only see up to 40 different shades. So after the images are manipulated and displayed, they're stored, and they're stored in many different types of media. We keep images on our console station in case we need the raw data. And then we also send the images to PACS. PACS is the picture archiving and communication system for imaging, and images are usually stored on PACS indefinitely. And they do that by storing all those images on large servers. So now that we have talked about how the CT images are acquired, I thought I would share some interesting cases with you. So here's a CT scan of the brain, and these pictures are not the best quality, so I do apologize. But here you can see this big, light, bright looking thing. That is actually a brain bleed. That's what we're seeing. And it's causing the brain's midline to shift. So you can see here, this midline shift. Over here on picture B, you can see a severe subarachnoid hemorrhage outlining all of the cisterns of the skull base. So all of these light parts that you're seeing are abnormal. Here's another interesting case. So here's a chest X-ray, and you can see that this heart looks kind of different because of where the arrows are pointing here. The heart's down here, but this looks like something else is going on. So they did a CT scan, and you can see a mediastinal mass right here. All of these arrows are pointing to it. So that's all this fatty tissue. So that's the kind of detail that we can see with CT. Here's another interesting case. This is a hemangioma of the liver. So what happens in CT is we give patients IV and oral contrast, and sometimes a different type of contrast, which I'll talk about later. But for this patient, we gave them IV contrast. And this first picture, there is no IV contrast at all. And we can see that because there's no brightness right here in the aorta. But you can kind of see that something looks different here in the liver, and that's where the arrow is pointing to. So that's a hemangioma. The second picture, this is what we call the arterial phase of the CT scan. And this is about 30 seconds after we give them the IV contrast. And you can see how this hemangioma looks way different than it does in the first picture, and it's brightening up and enhancing is what we call it. This third picture, is a 70-second delay after we give them the IV contrast, and you can see how it looks even different than the second picture. And that's called the venous phase. This last picture over here, number D or letter D, that's a delayed image. You can't really see too much, but it just basically washes out of the hemangioma, the IV contrast does. So the last interesting case that I'm going to show you is right here. You can see an appendicitis. These are really hard to see on CT. This is probably the best one I've ever seen. But see how this little loop right here just looks funky and different from the other loops? That's an appendicitis. So that most likely meant that the patient had to go and have their appendix out. And we can do that scan in about 5 minutes. So we can find out, what's going on with the patient that quick. So I also wanted to talk a little bit about what happens for a CT technologist during the day when you come in to work. So you come in the morning and you perform some QC testing on the scanner. Throughout the day, your goal is to produce high quality examinations for the patients. And we do this by making sure that we're doing the right patient and the right protocol. All the protocols are set up in the scanner, but we also have to administer contrast to patients. And we do this orally, intravenously, and sometimes even rectally. So we give them oral contrast, and that lights up their intestines and their stomach. And then we also give intravenous contrast, which lights up all the vessels. And also, as we just saw, hemangiomas and other things that are going on inside the body. So what happens when a patient has a CT scan? The patient goes into their doctor's office or they go into the emergency room and they have some sort of complaint. The patient's doctor will order the CT scan. That order is then sent to the CT department. The patient will go to the CT department and have the CT scan performed by the technologist. It usually happens in less than 20 minutes from the time that they arrive to the time that they leave. We can do a head CT scan even faster than that. After the scan is done, the images are sent to the radiologist. The radiologist will then interpret the images and send the results to the ordering doctor. The ordering doctor will then give the patients the results. And so that's basically what happens when you have a CT scan. Does anybody have any questions? So here's a question. How do CT scan records differ from X-ray records? So basically I don't know if that means the CT scan records different from the X-ray. So the X-ray, that is just a 2D picture. It's just one flash of the X-ray beam through the patient, and it's recorded on a plain film. The CT scan is several X-rays of the patient as the patient's continuously moving through the scanner itself. And these images are recorded or shown on the computer monitor. It's all digital now. So we do a CT scan and we get about 500 different pictures as opposed to an X-ray, which is usually only one picture. What's the different radiation exposure between the two? So that's a great question. An X-ray gives a very tiny dose of radiation. A CT scan gives about 100 times more radiation than an X-ray. Does anybody else have any questions? All right, well, I guess not. Thank you all so much for coming and participating. This was fun. I hope you learned a lot. Yeah, this is it, I guess. Thank you.